In the previous class, we saw the basic small signal model and the current voltage relationships for the drain current versus the gate source and drain source voltage of the MOSFET. In today's class, we will look at some simple MOSFET circuits and see what the small signal behavior of those circuits is. So, let us start off. The first circuit that we will look at is the common source amplifier. So, I will draw one version. As with circuits in general, there are many different versions of the common source amplifier. I will draw the simplest possible version. Where the source terminal is common to the input and output ports, and the drain terminal is where the output is taken, and the gate terminal is the input port where the input signal is applied. Now, at the gate port, the DC and AC signals are separated using a very large capacitor. I will show it as an infinite capacitor, but it is usually a very large capacitor. And before we draw the small signal, let us do the DC circuit analysis first. The capacitor is an open circuit, and therefore, the voltage at the gate, which I will represent as VGQ, representing the quiescent gate voltage, is nothing but RB by RA plus RB times VDD. As you can see, in this version of the circuit, we are generating the gate voltage from the supply voltage itself. The quiescent source voltage, of course, is 0, because in this case we have grounded the source voltage, and the quiescent drain voltage is VDD minus I naught times RL, where I naught is the bias current through the MOSFET. Now, what is this bias current? So, that is an additional DC parameter for the circuit. I naught is related to the gate source voltage in the following manner. Please note that normally to calculate the operating point for hand analysis, we do not consider the RDS of the MOSFET. So, we do not consider any dependence on the drain source voltage. And by writing this equation, we have also assumed that the transistor is properly biased in the saturation region. And of course, VGSQ is nothing but VG quiescent minus Vs quiescent. So, once VDD is known and RA and RB are known, you can find out the quiescent gate voltage. In this case, that also happens to be the quiescent gate source voltage, and the drain current is known, and therefore, the drain quiescent voltage is also known. So, we are done with the DC. The next step is to calculate the small signal parameters of the circuit. So, the small signal parameter of interest, so this is DC. For small signal analysis, the first step is to calculate the small signal parameters of interest. In this case, there are two parameters as we saw last class. The first one is the GM, or the transconductance of the MOSFET. So, this is a function of the device parameters mu n C ox W over L and the bias current I naught. And RDS is a function of lambda, and we saw last class that it is equal to 1 over lambda ID. If you know lambda, right, and the bias current, you can find out the RDS of the transistor. Now, once you are built the once you know the small signal parameters, the next step is to build the small signal equivalent circuit for this amplifier. So, the capacitor happens to be a short circuit because it is an infinite capacitor. VDD is signal ground, and therefore, the two resistors appear in parallel, RA and RB appear in parallel at the gate of the device. At the drain is where you take the small signal output voltage, and you have two parameters, one is RDS, the other is GM times VGS, which is the voltage controlled current source. And apart from this, you also have the load resistance RL. So, systematically the gate voltage is the small signal gate voltage is nothing but the input voltage Vs modified by the resistive divider formed by Rs, Ra and Rb. Now, as we know from our basic circuits knowledge, this means that we want Ra parallel Rb to be much larger than Rs, so that the gate voltage is approximately equal to the input signal voltage Vs. And this also means that the amplifier as the 2 port will have a Y11 which is almost 0, which is a precondition for large amplification, large gain. The next step now is to write the voltage at the output. The voltage at the output is nothing but GM VGS times RL parallel RDS, and with a negative sign of course, because the current is being pulled out of the node for a positive source voltage, and this is nothing but minus GM into RL parallel RDS times Vs, assuming that Vg is approximately equal to Vs. Therefore, the gain of the amplifier VO by Vs is minus GM into RL parallel RDS. If the circuit is designed such that RDS is very large, then the gain would tend towards minus GM RL. Let us look at a slightly different circuit. The next circuit that we are going to look at is the common drain amplifier. Since we want to move on to analog ICs, so we will look at just these two structures for amplifiers and then look at some biasing circuits also. So, if you look at the common drain amplifier, now instead of the source terminal, it is the drain terminal that is common to both input and output ports. And the gate voltage is biased at a constant voltage, again using a resistive divider. At the source terminal, you have a current source that sets the bias current through the transistor, and since you do not want very often you do not want DC current through the load, you have an infinite capacitor at the output side also, and the output is taken across the load resistance RL. Now, again we can go through the same procedure. We will write down the DC parameters for the circuit, the DC voltages and currents, then we will figure out the small signal parameters from the DC voltages and currents, and then we will figure out the gain of the circuit. Now, the quiescent gate voltage is again RB by RA plus RB times VDD, that happens to be the same as before, but this circuit is slightly different in the sense that it is now the drain voltage that is constant and it is equal to VDD, and the source voltage is figured out by subtracting the gate source voltage from the gate quiescent voltage. So, then the next question is, what is this gate source quiescent voltage? This is now a function of the bias current through the transistor, which has to be equal to I naught, and therefore, this gate source voltage can be written as Vt plus root of I naught over mu n Cox W over L. I have derived this last equation purely from the device current voltage characteristics, and therefore, the quiescent voltage is this expression. Now, one last thing to note as an aside, this parameter root of 2 I naught over mu n Cox W over L is often called the VD sat of the transistor or VDS sat of the transistor. This is nothing but VGS minus VT at the operating point, at the quiescent point. So, this is a very useful parameter for the circuit, as we will see going forward. This is also often called the overdrive voltage, because it is the voltage over and above the threshold voltage required for the device to conduct a particular value of DC current. So, it has many different names. So, we have figured out the voltages. Finally, of course, the drain current is nothing but I naught, because in this particular case, unlike the last common source amplifier, we have biased it using a current source. Now, let us move on to the small signal analysis. This was DC so far. So, again the first step is to figure out the GM, and since we know the current, we can figure out the GM, and as before RDS is 1 over lambda I naught. So, now we can draw the small signal equivalent circuit. At the gate terminal, the small signal equivalent circuit looks similar. On the output side, there is some small difference, as we will see. This is GM times VGS and this is RDS, but now it's the drain terminal is at small signal ground, and at this point the current source is an open circuit for small signal, and you have the load resistance RL. Now, we will point out that VGS for the transistor is VG minus VO. So, now we need to figure out what VG is. VG is RA parallel RB by RS plus RA parallel RB times Vs, and as we know, normally we want all of the voltage input voltage source to appear at the gate, and we will say this is approximately equal to Vs. And we know that will happen when RA parallel RB is chosen to be much larger than RS. In this case, VGS is approximately equal to Vs minus V naught. Now, we will apply KCL at the source node of the MOSFET, which also happens to be the output node. So, the current flowing out of the node is VO by RL plus VO by RDS. So, those are the currents flowing in this direction and this direction, and this should be equal to the total current flowing into the node, which happens to be GM VGS. So, now to make things simpler, I am going to write it in terms of the conductances. Note that 1 over RL is GL and 1 over RDS is GDS. So, you can write the equations in terms of the conductances. Sometimes it makes things easier to visualize. So, now, GM times Vs minus Vo is equal to GL times Vo plus GDS times Vo, and therefore, GM times Vs is GM plus GDS plus GL times Vo, and this gives us the expression for the gain of the device, gain of the amplifier. This is the ratio of GM to the sum of GM plus GDS plus GL. So, this is the common drain amplifier gain. As you can see, the gain of the common drain amplifier is positive, whereas the gain of the common source amplifier was negative. I think that is something you should remember. Please note the negative sign here, and in the case of the common drain amplifier, the gain is positive. What else can we understand from this? If GM were large, then the gain of this amplifier tends to 1. So, let us see what we mean when we say GM is very large. So, to do that, we will make one approximation. We will say that normally for a device, GDS can be chosen such that GM is much larger than GDS. In other words, what I am saying is the intrinsic gain of the device GM RDS is usually much greater than 1. This is of the order of several tens or maybe even close to 100, and therefore, GDS can be neglected with respect to GM. So, now I will write the gain like this, but now I can substitute for GL to be 1 by RL and now this tells you what GM means. So, when we say large GM, if you want to be more specific, GM should be chosen to be large enough such that GM RL is much larger than 1. So, for a particular load resistance, GM should be chosen large enough such that GM RL is much larger than 1. Also, please note that the gain of the circuit is normally never greater than 1. Similarly, there is a third circuit called the common gate amplifier. I leave the analysis of this circuit as an exercise for the viewer. Next, before going forward, let us look at some simple bias circuits using MOSFETs. You may remember from your basic circuits course that it is possible to use a current source to generate the required gate source voltage for a MOSFET. I am going to name these now that we have multiple MOSFETs. I am going to call them M1 and M2. So, now one of the things we will rely upon, as you will see, this becomes more and more important as we go ahead in the course. So, in analog ICs, we will assume certain things. On the same IC, devices with same width and length are nominally identical. This is not true for discrete devices. If I go to the market and buy a discrete MOSFET, if I buy two of them, I am not assured that they have identical behaviors. Whereas, if I design two MOSFETs on the same integrated circuit, I am assured that they are nominally identical as long as they have the same dimensions. What does this mean? This means the behavior of these devices, of two such devices, is identical with respect to the device parameters. So, they will nominally have the same mobility, same oxide capacitance and same threshold voltage. The other thing you can say is that the minute they are on an IC, they are very close to each other, and therefore, they will experience very similar temperature changes, and therefore, you can assume that the temperature dependence is also the same. In other words, if the temperature changes, let us say the temperature increases, normally the mobility of the holes or electrons falls with increase in temperature. In such a case, you can assume that if you have two devices on the same IC, their mobilities will change by the same percentage amount. And the other interesting thing about ICs is that this is not only true for the MOSFET, this is also true for resistors and capacitors also, which are the other two types of devices that we will use. Assuming that the resistor and capacitors have the same dimensions. Naturally, they should also be the same. There are many different ways of building resistors on an IC. When you say two resistors are identical, you have to use the same type of resistor also. Having said this, let us come back to this bias circuit and point out that, or figure out how the circuit will behave. I think many of you might have seen this in a basic analog circuits course, but let us nevertheless quickly write down the equations. So, I have called these devices M1 and M2. Our job is to find out the drain current of the MOSFET M2. So, to do that, to find out the drain current, we need to find out the gate source voltage. Note that both the devices M1 and M2 have the same gate source voltage, and let us say that voltage is VGS1. VGS1 can be figured out for the first device through its current voltage relationship. The drain current for M1 is nothing but I naught, and this is the gate source voltage for device 1. Note that this is also the gate source voltage for device 2, and therefore, this means that nominally ID2 is equal to I naught. There are several things we need to realize before we go ahead with some details of this circuit. The first assumption, or the first thing to note, is that it is not an assumption, M1 is always in saturation. This is because the drain source voltage for M1 is equal to the gate source voltage, and clearly the condition for the MOSFET to go into triode is go out of saturation into triode is for the drain source voltage should be lower than VGS minus VT, and this is clearly not, it is one threshold voltage away from that. Now, the second point is an assumption. We have assumed that M2 is in saturation because we have applied the same gate source voltage. That depends on what the drain voltage is. So, this our assumption is valid only if VD2 is larger than or equal to VGS2 minus VT. Which happens to be the VD sat of the transistor. As long as the drain voltage is large enough to keep M2 in saturation, the output current, drain current ID2 will be nominally equal to I naught. There is a third point to note, which is the effect of lambda. So, ID2 will be nominally equal to I naught, but there will be some delta I depending on the drain voltage. If VD2 was equal to VGS2, then delta I is 0. If VD2 is larger than VGS2, delta I will be positive, and if VD2 were smaller than VGS2, delta I would be negative, and therefore, the output current will be slightly different from the input current. This is clearly an effect of the RDS of the transistor. In other words, if I were to draw the ID versus VDS for the devices, so I have shown a slight dependence on VDS. What I will do, I will exaggerate that dependence to show it in slightly better detail. Now, on the same curve, let us say this corresponded to a gate source voltage VGS1, this curve. On this curve, M1 is located at a drain source voltage equal to VGS1. This is the operating point of M1. And that will happen at a current I naught. However, M2 is also on the same curve, but the drain source voltage can be different. If the drain source voltage were here, for example, clearly the drain current ID2 is going to be larger than I0, whereas if it were slightly smaller, the drain current would be smaller than I0. I hope this is clear. Now, the nice thing about this circuit is that you can now generate many copies of this current using just a single MOSFET M1. I have generated one copy here, but nothing prevents me from connecting this to a third MOSFET, generating a second copy of this current, and so on. I can generate as many copies as I want. So, the third thing about this is that I can not only generate copies, I can generate multiples of this. Let us say M1 had a ratio W over L. In other words, it had a width W and a length L. If I chose M2 such that it has twice the width 2W and a length L, then ID2 is given by this relationship. This is clearly 2 I0. So, therefore, I get twice the current here. This is exactly the same as putting two devices in parallel. Please note that. If I put two devices of width W in parallel, that will give me the same effect. Because each of these has a current I0 and the total current is 2 I0. Now, the last thing is that we can also generate fractional currents, because for example, I am going to show this on the same diagram in blue color. If I want ID2 to be equal to 3 by 2 I0, then all I have to do is I have to use a width 2W for M1 and I will use a width 3W for M2, then ID2 becomes 3 by 2 I0. In fact, if I use MW over L for M1 and NW over L for M2, then ID2 is equal to N over M times I0. So, you can create fractional currents. So, this current source is a very versatile, current mirror is a very versatile circuit. next we will see how this current mirror can be improved to give you better behavior with respect to the drain source voltage. In other words, we want the output current to be exactly equal to I naught instead of, so in other words we want to get rid of this delta I term as much as possible. We will look at that next.